I'm Peter Meckel. I work in the systems measurement and control area. Done a lot of research in motion control, especially as applied to any sort of manufacturing or production systems. Many modern robots now, if you try to move from one point to another quickly, you'll end up with vibration at the end point, which means if you want to do anything precise at the end, you'll have to wait for that vibration to stop.
For every robot, it's essential for the motion. So how to plan a motion with less vibration is critical for every move. So we are dealing with finding a sweet spot such that it's quick enough, but it still less vibration.
The two-link arm that I have here in the lab is a classic example of a system that's a little bit harder to control. If I move the arm from one point to another, the arm gets longer. That means the inertia element gets longer, even though the spring stiffness stays the same. So that means that essentially I change the frequency. And I change it not every once in a while, but I change it throughout the motion. And so what we're trying to do here is look at new strategies that will allow us to minimize the vibration, even for systems for which the vibrations are changing. Behind me is the two-link robot arm that I use as a test bed. This is actually a device that was designed and built in-house. Most of the parts were made by students. It consists of a shoulder and an elbow joint, much like a shoulder and elbow in our own arms. We also have encoders that measure the positions of each of the motor angles, encoders that measure each of the link angles. In addition to that, we also have accelerometers mounted at each of the links. So what we've been looking at for quite a few years is ways to design inputs to the motors, shape the motor commands in such a way that it minimizes the extent to which those vibrations are excited. And the way we do that in particular is we remove energy from those motor commands at the frequencies where the system wants to oscillate. Now we recognize that the frequencies are changing over time, so we have to be careful to design the input in such a way that we take into account that change in frequency. So what this allows us then to do is, in a horizontal plane, to look at the effect of flexibility on achieving good point-to-point motion while minimizing the vibration.
I started on this project when I was a junior year, when I was enthusiastic with the motion planning of the robotic arm, and then I continued to use it as my thesis project. Purdue, I love this place.